Okay, so for carboxylic acids, they're actually, I think, very unique that they're the only species where you can actually form an acid chloride in decent amounts. The reagent that I use for that is something that you should be familiar with. It's Sachal, or SOCl2. I can also treat them with acids, acidic concentrations with an alcohol to form an ester. I can go ahead and treat them with an amide or an ammonia with heat, and then I'm going to be forming, an amine and ammonia. I don't know why I always get those confused. And I'll be forming an amide. But what's interesting also is that if I apply heat to, say, a structure like this, I can end up getting a cyclic anhydride, which I think is just quite interesting, that I can do a dehydration reaction essentially by just adding a lot of heat. So let's talk about each and every one of these. The first one I wanted to talk about would be the Sachal II reaction. And I'm going to go ahead and just draw a stepwise mechanism for it, but it should be, I guess, kind of predictable and somewhat familiar if you remember. I think it was chapter 10 or 9. I don't remember. Species. And what's interesting is that, you know, it's very unstable. It doesn't look much different from any other type of, but both of these Cl groups, if we understood how unstable acid acid chlorides are, yeah, we have to put in, though, something that's even more unstable than an acid chloride, and this is the one thing that we have that is more unstable than an acid chloride. So the electrons are going to be attracted to the partial positive charge of that, and in doing so, it can't, sulfur, as big as it is, can't handle that, and you have an immediate removal of a leaving group, in this case chlorine. Alright, so this is arguably not the most stable looking species on the planet, and as you can imagine, it's not going to be. The book actually shows chlorine acting as a base to remove this. I don't really like that because you're forming hydrochloric acid. That's a pretty strong acid. I'm going to go ahead and just make the assumption that after we've added this, after we've had this reaction here, now I can't add this with this because this, I don't know what how basic pyridine is, but that's reducing my concentration of nucleophile in this context. Sorry. But if I were to, you know, add this afterwards, I feel like that would be a much more efficient reaction because you don't want to be forming chlorine, which is that's a hydrochloric acid that's very strong. So I'm going to go ahead and show it with pyridine, and that's what we had learned when we had talked about Pockle, Sachal, and PBr3. I think I made a video for that a long time ago. But anyways, deprotonation reaction takes place to remove the positive charge on the oxygen. And, you know, just like when we talked about Pockle, Sachal, and PBr3 with alcohols, we have now formed a really good leaving group in this reaction. So I think you can imagine what's going to happen. And whereas last time I think I had specified that it was a SN2 or SN, I think it was SN2, maybe it was, yeah, SN2 reaction. With this is a nucleophilic substitution reaction. So what happens is, as I had shown over here, and I don't know if I clarified it, but I have formed a chlorine anion. So I'm going to go ahead and just move this down here and just show what I'm talking about. The chlorine that I had formed, it's not the chlorine that's a strong reactant, it's just the fact that this is such a good leaving group that really makes this reaction proceed. I think a lot of these reactions, it doesn't say this, but I'm going to make the assumption that they're incredibly concentration dependent. Anyways, I have a chlorine attack here. This is going to move electrons to the top of my oxygen, and from there I think you know what is going to happen next. So as always, when we were at this stage, the lone pairs go back down. I believe it actually gets converted to be put in between as to forming a pi bond there, and that's the loss of your leaving group, thus giving us your final product. Alright, so that's my final reactions. One of the things that always really pissed me off whenever I was learning about Pockle, Sachal, and PBr3, and it applies to this as well, is the fact that this is classified as a good leaving group and this is just too unstable to isolate. But keep in mind the proton transfer reactions, even if I said I wasn't going to use pyridine, if I just used chlorine for this, proton transfer reactions are always going to be faster than any other type of reaction. So this is a great leaving group, but it's going to be deprotonated faster than you can have a nucleophilic attack. Carboxylic acids reacting with alcohols and water. And this is sometimes called the Fischer Esterification because, as you can imagine, we're forming an ester from a carboxylic acid. Also make note that we're adding catalytic amounts of hydrosulfuric acid. So let's draw out the mechanism. Time it shows this, well, it's not actually said here, and it isn't implied though, that whenever you have an acid, it's, especially if I'm saying catalytic amounts of acid, and a carbonyl compound, it's going to do exactly what every other acid has done ever. So just like before, when we had talked about acetal formation, we have now protonated the oxygen of our keto, or sorry, of our carbonyl, and this is going to form a very unstable species that is so unstable that even very weak species such as alcohol and water can react with it. So we have a nucleophile attack of alcohol. And so the oxygen having a positive formal charge, I'm just going to go ahead and draw it in gold to keep my color coordinations here. So we have the conjugate, in this context it'd be HSO4-, but it can be any generic base. We're not playing picky here. It's going to deprotonate the positive formal charge on the oxygen, thus giving us our tetrahedral reaction intermediate. And obviously us adding catalytic amounts of an acid, I'll just go ahead and clarify here, means that we have more than one equivalent at the very least. So we have yet another protonation reaction taking place. Next thing that happens is as you protonate it, you have a positive formal charge. I didn't show equilibrium errors, but all these reactions, anytime you're working with this mirrors the others, it's existing in equilibrium. But eventually, whenever the oxygen lone pair moves down here, water is a good enough leaving group on its own, we go ahead and have the loss of water. Didn't really leave a whole lot of room, but another conjugate base of our acid, of the catalytic amounts of, in this case, hydrosulfuric acid, comes along, and then you have a deprotonation reaction taking place to remove the positive formal charge. This is something that we've drawn over and over and over again. We're just changing up the story. Thus giving us our final product of our ester. Now, I didn't clarify this because I didn't feel like it was superbly important to mention, but every reaction that we're talking about here is existing in equilibrium because this mirrors the hydrate or in hemiacetal type reactions where you have protonation there and then a very weak species acting as a nucleophile. And while it should go without saying, obviously if I treat this with a base firsthand, this is going to deprotonate my carboxylic acid because carboxylic acids are, relatively speaking, very strong organic acids. And you're going to end up forming a carboxylate anion, which isn't going to do anything, and which anything is not even really worth mentioning, but the book makes the distinction of saying that. Carboxylic acids reacting with amines to form an amide. And this is kind of, I guess, a little bit different from the ones that we had talked about earlier. So carboxylic acids are acids, and then whatever it is that we're reacting with here, whether it's, you know, hydrogens or R groups, not really too drastic differences between the two, is going to be an acid-base reaction. So really what you're going to get usually is this reaction where you have a deprotonation of your carboxylic acid to form a carboxylate and then an ammonium. And so the way that we do this, the way that we avoid this, and this does happen, I'll just make a note that this does happen. I'll draw the arrows showing this. Charges, I've gone ahead and formed a salt. This is an ionic bond, quote unquote. And so the only way to really get this to form the amide, which is what I want it to form, is to, after that, add a lot of heat. Greater than 100 degrees Celsius will dehydrate my ammonium salt down to, and it doesn't really show the actual mechanism. I imagine it's quite violent. I'd hope to see it. But anyways, I end up getting myself an NR, or H. I think I'd shown H's, so I'll just go ahead and clarify that that's what I'm talking about. It's kind of inconsequential, though. NH2. So I've ended up forming myself an amide. The problem is that this is a really, really inefficient reaction, so I'm just going to write down here that it gives us a low yield. So it's really wondering why they even bothered mentioning it, but just know that this can happen at incredibly, I'll just make up how many, so it has to be greater than 100 degrees Celsius. It's a plus sign, plus 100 degrees Celsius of heat to get this reaction to go forward. So I guess a more effective reaction to convert a carboxylic acid into an amide is using something called, I'm just going to go ahead and put it over here, DCC, as a catalyst, I guess you could think of it. And I don't know if I mentioned this earlier when I was talking about heat, but adding the heat that we're doing that acts as a dehydrating agent. It just does it in such a low yield. But this DCC is also a dehydrating reagent. This is the overall reaction that I'm about to talk about. I have a carboxylic acid. The first thing I add is DCC. The second thing I'm going to add is going to be my amine. And in doing so, I have to make a note that my amine cannot be a tertiary amine. It can be a primary, a secondary, or an ammonia, but it can't be tertiary for reasons I'll explain later. And I go ahead and react this and I form an amide compound. So let's draw the individual reaction of how this works. All right, so this is really, really goofy looking. This kind of reminds me of the, I think it was the nitronium ion or something like that, that had very, this is, or maybe it was an oxonium, I don't remember. But anyways, you have two electronegative elements with double bonds to carbon, all of which are fighting for those electrons. And so this carbon here is going to have a very strong partial positive charge. The electrons in the OH group of the carboxylic acid are going to be attracted to that, and then doing so, carbon can't go over his octet rule, so I'm just going to arbitrarily break the bond on the bottom to show what it is that I'm talking about. Now, these R groups aren't necessarily whatever. They have to be cyclohexanes. I just don't have room to fit that into my pictures here, but keep that in mind, that the R group is equal to a cyclohexane. I'm going to say that a third time, that in DCC, the R group is a cyclohexane. So just keeping in mind that in a reaction, the overall charge of a molecule of your species doesn't change. We have a positive charge here that is also counteracted with this negative charge here, and they don't like that so much. And what happens is an intramolecular proton transfer reaction. And you could also, though, visualize this as, you know, we have this species reacting in equilibrium. We have carboxylic acids and amines running around fluently. We could also have putting protons on and protons moving off. Protons are shuffling. That's all that I really feel like is important that you know. So we go ahead and have an intramolecular, that's just the way I'm going to draw it, proton transfer reaction, forming what can only be described as the goofiest fucking thing I have ever seen, because you can't see it because I've substituted with R's, but these R groups are cyclohexane rings. And so we have this big goofy looking reaction intermediate that is pretty much, to me it almost mirrors that of a anhydride with an ester, I don't even know what, but it's very goofy, very unstable, and in doing so, it's highly reactive. So we go ahead and then this is when we add our amine to the situation. Just like before with this goofy ass thing, we have no changes in charges. The charge of a molecule hasn't changed. We've added the nucleophile attack, which has gone up, and I think you know exactly what happens. What goes up must come down, and that's just what we're going to get. So the lone pairs are going to move in here to form basically reform a carbonyl. And the oxygen, this is kind of hard to explain. The bond from the oxygen goes in from here. It almost jumps over, if you could think about it. There's a concerted step here, forming a pi bond essentially with this carbon here. Now that carbon cannot break its octet rule, and in doing so, moves a lone pair up. Electrons from the pi bond to form a lone pair on the nitrogen. Very, very quickly. And I can't, my book doesn't give any details about this. I don't know if this reaction happens at the exact same time, because this is a tetrahedral molecule. I could be thinking about this in 3 dimensions where I rotated this to be up there near that. But I'm just going to go ahead and draw it as a separate reaction as well. But very, very quickly, we have a proton transfer reaction of that nitrogen there with 2 lone pairs. That's an extremely strong base. It's extremely basic. Gosh, like an NH2 kind of basic. So that reaction is going to happen fast. I'm just going to go ahead and clarify that that happens really fast. And what you get out of this, as you can probably see, is that's our final product of our amide. And that's a very unique reaction that carboxylic acids can undergo. I like this reaction way better than having to heat things, although it's a pain to draw the mechanism from it rather than just saying that I'd add a lot of heat to dehydrate it. This gives us a much better yield than just using heat. I guess the only issue that I have with this is this kind of reminds me of the enamine formation and imine formation. I'm wondering if the whole thing here, if we have, say for example, carbons here that are not sp2 hybridized, that have things branching out on them with hydrogens, that those hydrogens could as well be deprotonated, forming a double bond there, but I guess that's kind of outside the scope of this course. Nevertheless, this is your final product. This gives us a very efficient reaction to convert a carboxylic acid into an amide.